Today's speaker is Shunta Arai from Tokyo Institute of Technology, who will be talking to us about quantum annealing for continuous function optimization. So Shunta, do you want to share your slides and make a start? Roughly half an hour, including questions.
Okay, thank you for giving me this opportunity to talk about our recent study. I'm Shunta Arai from Tokyo Tech. This study is collaborated with Hiroki Yoshiyama and Hidetoshi Nishimori. This is the outline of today. Let me introduce first of all, I will introduce our introduction and next move on to the model and the method, continuous function optimization by using domain-wide encoding. And next move on to the numerical results. And first we show the benchmark comparison between the classical continuous function optimization algorithm. And next move on to the comparison between the D-wave and the coherent QA made by the TEBD. And finally, we compare the result with the classical annealing algorithm. And finally we conclude our study. So let me introduce what is quantum annealing briefly. So all of you know the quantum annealing is a metaheuristic algorithm for ascertaining the ground state of the combinatorial optimization algorithm. The Hamiltonian QA is composed of two parts, which is one is the target Hamiltonian, whose ground state is a solution of the combinatorial optimization problem, and we add the driver term, the transfer speed term. And these two Hamiltonian is parameterized by the annealing parameter St divided by tau A. Tau A is annealing time. In the standard QA, we start from the initial state of which is the ground state of the driver term, which is the superposition state. The system, following this reading equation, we change in the annealing beta S from 0 to 1. The speed of the changing of the parameter is very slow. The system stays the instantaneous ground state, and at S equal to 1, we can obtain the non-trivial ground state of the target Hamiltonian. So the hardware realization of this algorithm is known to the DM machine. And the DM machine is expected to solve the combinatorial optimization problem faster than the classical algorithm at a real time, actual time scale. So this is the example from this paper. For the specific spin glass problem is directly implemented in the DM hardware. The DM machine can provide one-time benefit from the classical algorithm. So this is one example. The horizontal axis denotes the execution time, units a second, and the vertical axis denotes the relative difference from the best solutions, which is obtained from the parallel tempering. So from the right symbol obtained from the classical algorithm, for example, spin vector Monte Carlo, parallel tempering, and steep descent, and integer programming, and so on. The left one is left result obtained from the DM machine. So from this result, the 100 times speed up exists in this problem. So we often mainly focus on the discrete value optimization and perform the benchmarking for the discrete value optimization. And we can also consider the continuous value optimization. The continuous value optimization has many applications, for example, mathematical programming and machine learning. And so that as a solver, we can utilize the DM machine. And we expect the quantum fluctuations works in the continuous function optimization. But however, we have a problem how to represent the continuous degree of freedom in the binary quadratic model, which is available on the DF hardware. So in a previous study has proposed that the continuous function optimization on the DM machine can be performed by using the domain-wide encoding method. So they treated this potential function. The potential function has many local minima. and they compare the performance of the local optimization algorithm, for example, an Elder-May and conjugate gradient descent and the simulated annealing. And so they show that the machine performs better than the local optimization algorithm and the simulated annealing. These algorithms fail to find the global minima, but quantum annealing can efficiently find the global minima. This is a probability density plot. Yeah, but this old study is very qualitatively evaluated the performance of the QA. So in this study, this is the goal. We systematically investigate whether QA and has an advantage over classical algorithm for the optimization of the Rastrigin function. I will explain about the Rastrigin. What is the Rastrigin function? And next, we examine the potential of the ideal QA for the continuous function optimization with domain wall encoding. Next, we move on to the model and the method. And in this study, we consider the Rastrigin function. So the Rastrigin function is a test function for non-convex continuous function optimization. The functional form is like this. The harmonic potential plus the cosine term. And K is a spring constant. And the W0 and H0 is a control parameter of control the width and height of each local minima. The entire functional form is like this. If the H0 is large, the larger H0 gives a higher local minima like this. And this function has an interesting feature. Well, for example, if we solve the problem by using QA, so the direct simulation of the Schrödinger equation yields the scale of the regional energy like this. So the regional energy scales the power of decay with respect to the annealing time TA. So the exponent is larger than the SA, like this. So this is one example. Quantum annealing is more effective than the simulated annealing. So we adapted this problem on this study. And next move on to what is the domain one encoding. And in the domain one encoding, we consider the one-dimensional ferromagnetic Ising model with twisted magnetic field in the endpoint, like this. This is an example. And this model has a degenerate ground state with one domain wall, like this. Then the domain wall is a place where the spin direction is reverse, and we can the place where the domain wall occurs can be interpreted as a category variable like this. For example, this spin correlation -1, 1, 1, 1, the domain wall exists in this place, can be interpreted as a class 1. The next one is -1, -1, +1, +1, +1. The domain wall exists between this spin coupling. This spin combination corresponds to the class 2, like this, and so on. And by using this method, we perform the continuous function optimization. Next. The potential function we want to solve is represented by V. And this is a picture. Vx is a continuous space. And we discretize by using this Ising variable. And discretized potential function, the value of potential function is like this. And we, by using the Ising variable, and we associate the degenerate ground state with the corresponding the functional value, discretized functional value Vx. This is the example. This configuration corresponds to this functional value, and this configuration corresponds to this functional value like this, like this. So on the one-dimensional Ising chain, we directly represent the function value. So and we next move on to the model. And this model is only contributed to the place of the domain wall. And we assume two assumptions that Vx is differentiable and the delta x is enough small. The minimization of this problem can be mapped to the certain ground state of this Hamiltonian. This Hamiltonian composed of the one body term, only one body term, which is very easily to solve. But if we have to impose the domain wall condition like this, this is a total Hamiltonian we want to solve in this presentation. So next, move on to the result. First of all, we show the benchmark comparison with continuous function optimization algorithm with and DUA machine. So this is the setting, and the classical optimization algorithm, we run these algorithm with 10,000 differentiation condition, and we utilize the Apple ML bank. And this machine is the performance of this machine is comparable to the workstation, which was used in the old benchmark study in the discrete value optimization. And we utilize the DF2000Q because the DF2000Q has the best performance in the other version hardware. And we sample 10,000 samples per run, and we fix the embedding. The hyperparameter is like this, and we set the system size n equal to 200 to 11, which is enough to large to represent the entire function. And also all errors are computed by the bootstrapping. This is the result. First, we consider the higher energy barrier, H0 equal to 1. So this is the horizontal this figure is, in this figure, the horizontal axis denotes the execution time, units a second, and the vertical axis denotes the ground state probability. And the left result obtained from the local optimization algorithm and the nailed made and conjugate gradient descent. And the right result obtained from the global optimization algorithm, Bayesian hopping and differential evolution. And the purple symbol obtained from the DF machine, the average DF machine, the average result of the DF machine. And the pink one is the best result in this, the average result. So from this result, the performance of the DF machine is comparable to the global optimization algorithm around 0.7 to the 0.9. But for the global optimization algorithm, as we increase the execution time, the performance is enhanced. But for the DUA, increasing execution time or annealing time does not improve the performance. So the performance saturation exists in the DUA. And we also consider the lower energy barrier case, H0 equal to 0.2. So the classical algorithm can efficiently solve this problem with a lower energy barrier because each energy barrier is easily hopped to the another local minimum. So the classical algorithm is easy to solve. So the performance of the D machine is almost the same for the problem with the higher energy barrier case. And we also we can also see the performance saturation in this problem. Next, we move on to the comparison between the DUA machine and the coherent QA. In the larger annealing time or large execution time region, the performance saturation exists in the DUA. So we investigate the reason. So why the saturation exists in the DUA. So So in order to investigate the existence of the saturation, we investigate the dependence of the observable obtained from the ideal noiseless QA by using time evolving block decimation algorithm. And we also compute observable and compare the DUA result and the coherent QA result. And we compute three observable. One is the kink density, which computes the density in the number of defects in the spin chains. And next one is residual energy. And the last one is ground state probability. But this is the DUA result. The vertical axis knows the kink density and the residual energy. The horizontal axis knows annealing time, units are microsecond. And from this result, the observable shows polynomial decay in short annealing time region from 1 to 10 microsecond. And the exponent decrease as we increase the value of H0. So this means that the smaller exponent needs to more annealing time to satisfy the single domain wall condition. But if larger, higher energy barrier case, we cannot all sample satisfy with the single domain condition from the DUA result. Next, we move on to the residual energy. And residual energy has also the polynomial decay in the short annealing time region. And in the long annealing time region, the exponent gets very small. This is due to the decoherence and the thermal noise effect. So from this, as we increase the annealing time, we can not, the quality of solution cannot be improved. Next, we move on to the coherent QA. Vertical axis is the same, but the horizontal axis is annealing time. The unit is coherent QA time scale. So from this figure, we cannot see the clear H0 dependence of the observable compared with the D wave. And in the long annealing time region, TA is larger than 2000. Rho equal to 1 divided by n holds regardless of the value of H0. And we consider the time to reach the rho equal to 1 divided by n. So this time is correspond to the TA equal to 53 nanosecond in a real time scale. So this is a very fast anneal, and can be this is very fast annealing, and can be accomplished by the rho equal to 1 divided by n. And we also consider the residual energy. So in the long annealing time region, the residual energy also decreases. And the ground state probability approaches to 1. So in the coherent QA, as we increase annealing time, the performance is enhanced. So this is one take-home message. That if the coherent QA is realized, the optimization of the algorithm Rastrigin function works in the real hardware. So next, move on to the comparison with the classical annealing algorithm. And we perform the three classical annealing algorithms. One is the symmetric annealing, symmetric quantum annealing, and spin vector Monte Carlo with transfer speed update. And all algorithm is we utilize linear annealing schedule, and each observer are computed from the 20,000 samples. So as first we show the result of the simulated annealing. The horizontal axis is a Monte Carlo step. The observer shows a polynomial decay in the short from 2 and 100 Monte Carlo step. And these observable depend on the value of H0. So this is reflected on the fact that estimated annealing is driven with the thermal fluctuation affected by the height of the local body. And the DM result are close to the simulated annealing result. And next, move on to the simulated quantum annealing. And the simulated quantum annealing, for all value H0, rho converges to the 1 divided by n. So that in a large anytime region, all samples are satisfied with the single domain Born condition. And also residual energy, even in the long anytime region, has polynomial decay like this. So the qualitative behaviors are the same as the simulated annealing, since the observable depends on the value of H0, but it's different from the coherent QA. So and also a simulated quantum annealing suffers less performance degradation compared with the simulated annealing and D-wave, and the higher energy barrier, because possibly by the simulating quantum tunneling effect. Let's move on to the spin vector Monte Carlo. So the spin vector Monte Carlo, in the case of the H0 equal to 3.0, the King density and the residual energy has a plateau. So the dynamics of the spin vector Monte Carlo is more affected by the higher energy barrier in this case. But for in the region, rho equal to 1 divided by n, the spin vector Monte Carlo gives the largest exponent of the residual energy in the any other annealing algorithm except for the coherent QA. So the exponent is -1. It's very it's the largest exponent. But we consider the SVMC as a practical solver. The actual smaller absolute value absolute execution time is the important, not just for the larger exponent. So we need to investigate the actual annealing time. So this is the actual execution time comparison. The vertical axis is the King density and the ground state probability. The horizontal axis denotes the execution time, units a second. So from this result, this is the ground state probability, and this is the best result obtained from the D-wave, PZS equal to 0.124. From in the short time region, 0.4 to the 0.9, the D machine is the best choice in this region. It's very fast anneal and can solve this problem in this small region. So from this result, the performance of the DA will be enhanced by the reducing noise. So if we can realize the noiseless device, the performance is enhanced like this. And we reconsider the result of the differential evolution and the Bayesian hopping. These results take ground state probability is larger than the 0.9. It approaches to the 1 in 10 seconds, from 10 seconds to the 100 seconds. But the classical algorithm about 0.3 or is less than the 0.3. So from this result, the classical annealing algorithm are similarly less effective than the global optimization algorithm. This is the second take-home message. Let me conclude our study. We perform a benchmark of the Rastrigin function between the DM machine and the classical algorithm. And the DM machine, the results are comparable to the performance of the global optimization algorithm in a limited time region. but in the long time region, the performance saturate due to the decoherence and the thermal noise effect. However, in coherent QA, the performance improves as we increase the annealing time. So this is the take-home message. If the device operates coherently, the hardware realization of QA has the potential to outperform the best classical algorithm. Thank you.
Good, thank you very much, Shunta. Very nice presentation, lots of interesting things. And we have some time for questions, if anybody in the audience has questions. Maybe I can ask a question. So the number of spins you use in your domain wall encoding, you said was 211 at one point.
Yeah.
Where does that number come from? How do you pick that number?
How do you pick the number?
Why are you doing 11, not 100?
Because the larger size problem is difficult to solve in the D-Wave, and this size is a larger size problem cannot be simulated on the TEBD simulation. So this is the largest size and can be available in the TEBD in our computational resources.
So I'm looking at your domain wall encoding, and you have the two body terms. Can you go back to page 11, please?
Yeah, two body term. Yes, only two body one. Yes, and one dimension only has a one dimension structure. Yes, can be
page 11, please.
Easily 11. Okay.
Yeah, so you have two body terms in your domain wall encoding.
Only two body term. Yeah.
And this is an all-to-all interaction over these 211 qubits, or
no. This problem can be directly implemented on the deep hardware.
Interesting. Okay, and that's with the is this Chimera or the other one, that like Pegasus?
Yes.
Is it Pegasus or
no, Chimera.
Chimera. Okay, interesting.
The Chimera is better than the Pegasus and Delphi topology.
Okay, good. So
comparison is performed on our paper. So if you are interested in the result, please see please see our paper. Yeah.
I think the I don't understand enough about the encoding of the domain walls to comment, but so the 211 is on a 5,000 or a 2,000 qubit machine.
5,000 to 2,000 Q.
Okay, fine. I had one more question. So
okay.
Towards the end of your presentation, you were talking about DE and BH.
B and okay. B and BH. Yeah, hi.
Oh, okay. Yeah. But right at the end, you said that DE and BH were achieving a ground state probability of 0.9, if I remember rightly.
Yeah, this result, yeah. From 10 second and 100 second BH and the differential evolution achieve nearly equal to 1.
So do you think there is the possibility, even in the coherent regime, for D-Wave to compete with that result?
Yeah. So if we perform in the execution time, the annealing time is not dominant because we have a lot of time because computational time is very dominant in the D wave.
Yes.
So if we realize a coherent QA, a coherent regime, we can obtain the solution from the same time region at from 0.7 to the 0.9 in the DA we can comparable to this line, maybe maybe.
Okay, any other questions from other members of the audience? Well, if not, let's thank Shunta Arai one more time. Thank you very much, Shunta. Very nice presentation.
Yeah.
And I look forward to seeing everyone at next week's seminar. I can't remember who's giving that off the top of my head, but look forward to seeing you then. Bye-bye.
Thank you. Bye.